Thank you, Catherine, for this nice introduction, and good afternoon, everybody in the audience. Fortunately, I have to make it in English, and I cannot do it in Chinese language. My name is Oliver Baudson. I'm Managing Director of TSK Flagsol in Germany, a pioneer company active for 30 years in the CSP market, and we have implemented the first solar power plant in Spain under Zone 1, first time in the world with storage, and we are now the first company in the world to present in Morocco the first really and fully integrated CSP PV hybrid power plant. All other power plants are only co-located plants without a full integration. Actually, I will not only speak about the Morocco project, I will have a second part in my presentation where I want to show you how we in Germany try to complete our energy transition from traditional power generation to renewable power generation with the help of CSP storage technology. Yeah? But please follow me first of all through some marketing slides. Today the German company belongs to a Spanish group in the north of Spain, TSK. They are a worldwide active EPC contractor, the field of 1,000 people, 1 billion of annual turnover, and with international activity. So besides the CSP, where we have together almost 1 gigawatt out of worldwide almost 6 gigawatt installed, we are also active in other renewable energy technologies. We are active in conventional power generation, in material handling, oil and gas, and other industries. So coming to Noor Midelt, which is the very first of its kind of this hybrid, integrated hybrid type. I have always to send my congratulations to Morocco, who have structured such an intelligent and smart roadmap for introducing into their country a very smart, modern power generation mix. First, let's have a look to the stakeholder structure in this project. We have here on the right side the financing institutions. We have here the SPC, led by France's EDF, together with Mazda and a local company, and of course Baudson is part of it. This SPC sells the cheapest energy out of a CSP power plant ever to the off-taker, which is a Moroccan entity via Baudson, who sells it then further into the Moroccan grid. And that is really, in our view, world-changing technology approach, and that will certainly find in many places its followers. So we as TSK are the nominated EPC contractor and technology provider, and of course we will comply with the local content requirements which are set forth in the contract. So some words to the configuration of the plant. We have altogether a total installed capacity of 800 megawatt out of CSP and PV. We have AC plant capacity of around 200 megawatt electrical. We have an AC plant capacity in the night production that is contractually instructed of 80% of the day production. We are using our most modern helio trough design in the solar field. Our storage capacity is designed for 5 full load hour equivalents. The storage system is a combination of traditional molten salt storage and battery storage. The annual yield in the project amounts to 1.2 1.1 terawatt hours per year electrical. We have a footprint of almost 1,000 hectares. We are using dry cooling, no water. And the water consumption, I noted this here just to show that that the cleaning doesn't take so much water as usually assumed and colportated in media. So we have 90% of the water consumption for the turbine, and that is not the big amount which is here needed for the cleaning. Only 10% is for cleaning, indeed. So the auxiliary power consumption can almost covered by the plant itself. So we have almost a 100% coverage ratio. Here we have, you can see the dispatch profile of this particular plant. You see the orange line, which is really the dispatch profile. The generation starts in the morning, and then it is brought up to 100% of the nominal load, which is in this case, as I told you, around 200 megawatt. It is stabilized during the day, and when we start the night operation after sunset, we go down to 80% of the nominal load and empty the storage during 5 hours. This limitation of 5 hours is just a limitation in this specific project, because in Morocco they have this evening peak until midnight, and afterwards they do not need the power anymore. So that was a restriction coming from the project, but in theory you can design the storage to such an extent that you can continue the operation until the next day without turning down the plant. Yeah? So what does mean the dotted line in yellow? That is the portion coming out of the PV which is exceeding the nominal load, and we are not allowed to evacuate it into the grid. We are obliged to dump it or to curdle it, but that wouldn't be so intelligent, I think. As you can see, it is a big amount of energy. And this energy is taken to thermal and to other storage elements, and can then be used after sunset. So with that, we have, in the end, because we are using only mature technologies, PV, CSP, and storage, all mature technologies, we have a bankable solution. That is very important. And as I have shown you, with 6.2 euro cents per kilowatt hour, we have also a very competitive solution. More competitive than many fossil power generation facilities can be. We have 5 hours of dispatchability, and as I said, that can be extended to 24/7 if required, not 24/7. So, as we have here rotating masses with a turbine and a generator in the grid, we have also services for the grid stability and frequency stability, unlike other renewable energies such as photovoltaic and wind, which are imposing disturbances to the grid. So we are avoiding with this dispatchability redispatch cost. I will come back in my second part to that and explain how big this can be and how important it is that we have generation facilities which do not require dispatch. And of course this generation facility is 100% CO2 free and fully renewable. So in future, we believe with maturity of the technology, and certainly also in cooperation with Chinese partners and suppliers, we can even further decrease cost, and our target window in the future is to put power generations with cost between 4 and 6 euro cents per kilowatt hour in convenient places. So with such a solution, in solar countries, a 100% renewable energy mix comes through and is possible today without destabilizing the grid. And that is, for me, the important message to bring around. We can go ahead in putting more renewables to our grids. This technology also allows really large-scale storage and long-term storage, not yet seasonal, but at least a couple of days in theory. So that is helpful and that is affordable, in contrast to pure batteries, which will not yet, and certainly not in the next 10-20 years, make it at the same price. So, secure energy, I mentioned it already, and we can also go for large power capacities. We have here 200 megawatt dispatch. We can certainly go to 300-400 megawatt easily. Last but not least, hybridization is not only possible with PV. You can also do it with biomass, with waste, and other technologies. So with that, I want to conclude my first part of the presentation, and I want to share with you now some ideas we are considering in Germany in order to facilitate and promote the energy transition in Germany. As you know, we are stepping out of coal and nuclear, and we have to fill this gap with other technologies. And one idea I want to present here, but please follow me first to some basic considerations. So you can see here on the left-hand side the situation in Germany. We have around 200 gigawatts of installed capacity, half of it being renewables meanwhile, and half of this is volatile energy. So we have an issue here, and that means we have in terms of energy generation, in terms of kilowatt hour, we have 30% renewable energy share in our grid, and that brings us already to some limits where we have to see how we manage it and how we can get control over it. Yeah, at the same time, while increasing renewable energies and raising these grid problems, we have congestion costs raised from annually 50 million to today 1.5 billion euro. And that is a hell of money what needs to be avoided. So there is a full bunch of theoretical and possible solutions to manage volatility. Of course, we could say we stop introducing volatile energies, but PV and wind are so nicely cheap that we should make use of it. So we can, of course, introduce more non-volatile energies such as CSP, but unfortunately in Germany we are kind of limited due to lack of ENI. So what we do is actually curtailing, putting huge capacities and putting huge amounts of power generation into the grid, and then if there is excessive capacity we curtail it. But we have to pay it in Germany via the EEG, the Renewable Energy Law, although it is not produced. So it is only a partial solution. Then part of the solution is grid enhancement, but population in many places is very reluctant to accept a substantial grid enhancement. Demand-side management, of course, is something which will help, but also that requires the consumers to adapt their behavior, and that is also not always wanted. And we have all the bunch of power-to-X solutions, and last but not least, of course, storage systems. And I want to show you one storage system based on the CSP technologies, storage technology, and we enhanced this by equipping it with electrical heaters. So here you see the basic concept. In case we have excessive renewable energy amounts in the grid, instead of curtailing this potential, we take it now into the electrical heater and then use molten salt coming here from the cold tank, being heated in the electrical heater, being stored here, And then, when there is a demand, we can bring this heat here to another heat exchanger and provide it to any kind of heat consumer. So this can be a district heating or district cooling. This can be industrial process heat. And, of course, this can be a re-electrification of a ring-kind cycle or others. So, what we are investigating right now in Germany is very concretely to make use of this type of storage technology to convert coal-fired power plants into giga-storages. So the idea could be, again, to take excessive energy from the grid, put it into electrical heaters, store it, and make it available here at these heat exchangers. And then this heat exchanger, this heat source, will then in future replace completely the coal firing, but the complete power block can be reused and adapted to the needs of this heat source and continue to be operated. So, if we have a look to the evolution of the curtailed energy in Germany, we come to the conclusion that we have an annual curtailment of 5.5 terawatt hours. That is very much, and we should avoid that, or we should find a way to make use of that. And here we have done a kind of example with very rough figures and estimates. We were saying let's assume that we convert a block of 500 megawatt electrical, a coal-fired power plant. We will introduce a storage operation duration of 10 hours. We will achieve with this technology turbine efficiency of 45%. Maybe if we can in future play a little bit with higher temperatures, we can approach the 50%. We have foreseen a storage capacity of 5 gigawatt hours electrical. We have an electrical charging of 900 megawatt, and we have a discharging capacity then of 1.1 gigawatt. Then the annual yield, we assume here 100 cycles per year, will then amount to approximately 500 gigawatt hours per year, which is corresponding to approximately 10% of the annual curtailment amount we have in Germany. And the rough first approach results in an investment for such a conversion of around 500 million. So if we continue this easy and simple calculation, that would require around 5 billion investment to cover the entire curtailment. But if you compare it to our annual cost for congestion management, being 1.5 billion a year, then we could have a payback period of only 3 years, what is not a fully unrealistic approach. So, this technology is feasible because it is mature, it is applied, it is used in CSP plants already. The technical infrastructure of coal-fired power plants is already existing and we can reuse it. We will dismantle and stop and scrap them anyway, so let's find a way to give them a second life. Compared to annual incurring congestion cost, the required investment I showed you before appears to be reasonable. We will not have to dismantle these power plants and we will save the scrapping. We will maintain largely the employment and the surrounding service industry, what is also important for a country. And we will make use of a substantial part of renewable energy, which is today curtailed and paid according to our laws. And these plants will also give a significant contribution to grid stability, because
We also will operate here rotating masses instead of volatile renewables. The volatility is kept by the electrical heater, and then the system returns very stable energy, and that is also a very important feature of such a solution. So with that, I want to conclude, and I hope you found it interesting, and I thank you for your attention.